Okay, so go ahead with the variance now. So by definition, the variance denoted as sigma square equals, or another way is V of y, we're still talking about a random variable y, equals the expectation or the expected value of that random variables minus is mean or expected value, now denoted as the Greek letter mu. Now, but you ultimately understand that is EY. Now, everything in the brackets square, and then finally close the curly brackets. So what is that? It is the weighted average of the square distance of every possible outcome of this random variable y from the mean. So the distance of each possible outcome from the mean, square, and then take the weighted average of them, or the expected value of them. So why square? Because otherwise, if you take it as it is, can be negative or positive, right? If the distribution range from negative to positive values. So in that case, if you don't square it, positive and negative value may or can cancel out one another and then get distorted. So that's why they square to avoid this issue, and that's exactly the same idea behind the so-called sum of square residuals that you have known from OS regression. Okay? Now, some important results with the variance that you should know. Let's denote it as the first thing is if we use this definition, minus mu, everything square, and then we distribute, open this bracket inside by using a popular equality, at will equals the expectation of y square minus 2y times mu plus mu square. And then we can use the operation, the linear operation of expectation that we have seen before, to arrive in a further interesting result. So this is all linear because it's just minus or plus, so I could write it again. The expectation of y square minus this part. Now pay attention. 2 is a constant. I can put it out of the expectation operator. Mu equal to E y. Like I said, this is a theoretical parameter of the distribution. It also means now you can treat it as a constant. And as a constant means you can put it outside of the expectation brackets, right? And then finally plus, again because it's constant, the square of it is also a constant, therefore the expectation of the constant is the constant. No need for E with curly brackets over there anymore. So therefore at the end you would have y square minus 2 mu, and then EY against equal mu, right? So mu square. And then plus another mu square equals minus mu square, right? Okay, so this is the first result. The variance of a random variable equals the expected value of that random variable square minus is the square of its expected value. Sounds messy, but try to remember that. The second thing. Again, we can apply the linear operator of expectation for a linear function of that random variable plus b now. What is that? A squared, this is on your slide, now times the variance of y itself. To see y, let's first denote a function gy as ay plus b. Now, then let's go ahead calculating the expected value of gy. We can denote mu j equals, because it's here linear operator, right? The expectation of ay plus b equals a expectation of y plus b. Okay, let's keep that in mind. We need that later. Now, by definition of the variance, we have also v of jy, right, equals the expectation of here jy minus mu y, sorry, mu j, not mu y, square, right? So this is just the definition of variance adapted to the function j. Let's do it further. So that will be jy square minus 2jy times mu j, right? Plus mu j square. So that's what it is. Don't forget the curly bracket. Now, and we could open it out already. Again, thanks to the linear operator. So, expectation or expected value of jy square minus, now again similar to mu j, you can put outside already because it's all constant, right? Given that the expectation of y is a constant, times the expectation of jy, then plus, because mu j is constant, its square is also constant, no need the expectation operation there, mu j square. Now the only part we will have to take care is this expectation of jy squared. Then that expectation we can also again plug in back the ay plus b everything square minus 2 mu j times, you can plug in here already the expectation of jy, but we can first do it like that to simplify similar as above. I come back after cleaning it. Let's continue from this part here, right? So now we already know that the variance of the function j of y would be equals to the expected value of the square of that function minus the square is expected value, like before, similar. And then now the next step, let's plug in the value of the j. Plug back the thing that we named before, namely a y plus b, and open everything out to see what happened now. So b jy equals the expectation of, now, so now you have this using the same equality like before, a square times y square now, plus 2ay times b plus b square minus, we could already plug back the mu of j here as a expectation of y plus b everything square. Now, and I will also denote this ey as mu y. Now, so make it shorter for us. Again, linear operator. So constant move out, a square times e of y square, right? Plus 2ab times expectation of y plus b square is constant, so no need for expectation over there, just itself, minus, now let's have this as a times mu y square, a square, sorry, plus 2a mu y square, sorry, no square here, times b plus b square. Everything's still in the bracket. Now you have to pay attention to those brackets, otherwise you get the wrong algebra. Okay. So now here, let's spend a moment on it. You have a square times expectation of y square. Let's rewrite it. Sorry, cannot cancel out that. Right? And then we would have plus 2ab is y expectation. Here we could write mu y already. And if you pay attention on this, here you have 2ab times mu y. Inside you also have the 2ab times mu y, but with a minus over here, so they cancel out. Now, I will cross this slightly over here, so they cancel out. Okay, the next thing is b square over here. Inside the bracket exactly, you also have b square. Cancel out. So the thing outside of the bracket is already simplified, but in the bracket you still have this one. So you have to minus a times mu y squared. And we could factor out the a square. Then inside the bracket you will have e y squared, the expected value of the squared y, minus mu y squared. And what is this? Inside, which is exactly the thing that we have shown before, the variance of y by definition, right? So that means I could write here again AY plus B was shown on your slide. One last thing. One last line on that slide is now it becomes tricky with the unit of the sigma square, the variance, because it's not the same unit as the expectation on the random variables, right? So to make it somehow easier to interpret and to think about, they came to the concept of standard deviation, which is denoted as sigma, which is nothing else than the square root of sigma squared. Now, called standard deviation, and it has same unit as y. Sorry, y is there. No? Then to put it in the formal mathematical notation of the variance. Now, so here the variance of y in the discrete case, like said before, is the average, the weighted average of all the square distance of every possible outcome from the mean. So now this is the distance from the mean of every possible outcomes. You square it and then you weight it by the probability, right? So that's for the discrete case. And for the continuous case, we replace the sum by the integral operation. And the thing inside stay the same, y minus mu square times fy. However, fy now is the density function when y change from minus infinity to plus infinity. Now let's also talk quickly about those higher central moments of the distribution. Quickly, because I have not so much to add compared to what you have seen or what you have gone through in the winter semester. Okay, so normally in a very general way, the case central moments is denoted as the expectation of y minus mu to the power of k. Now, this look already very familiar because with the variant case we have y minus mu to the power of 2, no? And you can go for even higher moment. So we have seen the first central moment when k equal 1, no? So that's the mean, the first draw moment, so it's also called. The second central moment when k equal 2 is the variance, no? And then we have the third central moment to characterize the skewness, whether how much symmetric or how much asymmetric a distribution is. And then the fourth central moment is the kurtosis. So how much is peak at the highest level. Okay, the peakness of the distribution. So that you know already. Just have a funny example talking about skewness in the median. The story is about one person. He found he was diagnosed with a very rare type of cancer. Then he asked the doctor, what is the average survival rate or survival time of this type of cancer? And the doctor responded to him that 8 months is the median survival time. So 50% of the patients will live longer than 8 months. However, 50% of those patients will die before 8 months. Then I asked my friend, okay, if that's for you, what would you do? And my friend responded that, okay, I would spend all my money, do whatever I like, enjoy life in the remaining time. So here, the point is, what if the distribution of this survival time skewed? No? So it can be that, for example, it look like this, the distribution look like this, no? With a very long tail toward the right, meaning 50% of the people died somewhere before 8 months, right? However, those who survive, they will live a longer time. It's hard to determine how long they will live. Maybe they will make it through like normal people who don't have that cancer, right? Until 70, 80, 90 years old. So, and the medium is just telling you about 50% of observation falling below or above that point. What if you actually, those who survive longer than 8 months and make it until 90 years old, and you spend all your money already? Huh? Therefore, sometimes in this case, we will have to look at how skewed the distribution is and what's the mean of it. Now, okay, now let's go back again to the dice example and calculate the sample mean and also sample variance of this sample to see how it can be different from the theoretical expected value and variance that we have. But before that, let's put it down here, the population variance or the theoretic one that I just mentioned now. So by the definition, the variance of y, which y being the random variables of throwing the dice, equals the probability of the first outcome times the first outcome, 1, minus the mean, remember 3.5 square, no? And move on to the next outcome, 2 minus 3.5 square, so on, so on until the sixth outcome, so 6 minus 3.5, right? Everything square. If you have calculated it correctly, then it should be approximately 2.92. Okay, so with this in mind, let's go to R and see how the sample might look like. So here is where we stopped previously with the dice, right? We have a sample. Now let's plot again the frequency and the fraction of the outcomes now, and then we calculate the mean of this sample. You can see here 3.5 to 1, pretty close to 3.5, right? And when I said 3.5, I mean 3.500 now. And then the variance of the dice is of our sample is 2.81, whereas theoretically we have 2.92, right? So pretty close, but not the same. Why? Because you did not observe these outcomes from 1 to 6 with equal frequency. Some appears more than the other, right? Even the dice itself would not know before every time you throw it which face will be up, right? So that's the randomness of the action. Okay, to see how different it is, let's repeat the experiment again for another example. Now it will be different, and then we calculate the means, 3.52, the covariance, the variance, just the same command like covariance, which we will learn next section, but for now, that's the variance now. So 2.93 is already closer to the theoretic one. Let's do it again, dice, and then calculate the third sample mean, again 3.21, but now the variance reduced to 2.77 something now. So each time you draw a random sample or you do a random experiment of that variable, you will obtain a different sample even though you repeat it the same number of times, right? So therefore, the mean and the variance of the sample in this case only reflect the average of the weighted average of the outcome in the case of the sample mean that you observe. It didn't take into account those outcomes that you don't observe but may occur if you repeat it like to infinity time, right?